So yeah, so this is the last time you'll be seeing me here giving talks, and this is going to be an interactive exploration of EmitCactus. So we encourage everyone who's interested in taking a look and trying to use it for something to to check it out. And this is supposed to be one of those interactive sessions where I don't want to show you guys my email. Sorry about that. One of those interactive sessions where we do some stuff and hopefully you guys try to do the same things we're doing. And why doesn't this? Thank you. And you just like interactively implement something, right? So here in your folders, you should probably have a file which is called EmitCactus.ipy notebook. And my suggestion is that you use this notebook as like a starting point and as a reference to what we're going to try to do here today, right? So I was thinking of some interesting exercises that we could do, and we could do the wave equation again if you want to try and do the wave equation in a different way than what we're doing in this notebook, you're welcome to do so. Your main reference material is going to be found here in this notebook, right? I need to remind myself, how do I define a thorn? How do I declare variables? How do I add parameters? And so on and so forth, right? But the exercise that I wanted to propose today is that we implement a slightly harder version of the wave equation, which is a wave equation which is capable of being evolved on top of a non-flat background metric, right? And so for this, I'm going to use this paper here, which has absolutely nothing to do with the wave equation specifically, but it gives us the form of the wave equation we are looking for, right? So this paper, if you guys want to look it up on Google, it's called A Multi-Block Infrastructure for Three-Dimensional Time-Dependent Numerical Relativity, right? And my exercise, the proposed exercise for the session would be for us to try and implement what's in equations 5, 6, and 7 here, right? So this is still the wave equation, nothing more complicated than the wave equation, but we got some interesting features here, right? So for instance, given that this could be evolved on top of a non-flat background, we have to import some quantities from ADM base X, meaning we have to import the shift, and we have to import the metric, and we have to compute the determinant of the metric, and we have some tensors here, right, that need to be contracted and defined, and so on and so forth, right? So this would be the proposed exercise for today. And to start, let me go back here to my notebook menus. I think people probably don't have this specific notebook, but I have here, of course, I have a solution notebook, right? But the idea is for us to try to go through this together, right? So I never had one of these live sessions before, so I'm not going to say that I really know what I'm doing, but I guess this is the time that we try to start coding. And like I said, if you want a reference on where to start, right? Of course, we start by importing the EmitCactus stuff, right? The EmitCactus package itself. And we may also have to import some definitions. So given that the initial data that we're using here in this notebook is a plane wave initial data like thing, I suggest that we keep using that. That's probably just easier. And first steps would be, of course, defining our thorns, right? Setting our derivative stencils, and declaring our grid functions. So I'm going to try and do a picture-in-picture here where we can get the equations we're trying to solve. Right, and let's see if I can, I can close this. So, we can get some reference and side-by-side of these things, right? And if you're all EmitCactus specialists by this point, you should probably do this in no time. So I'm going to give you guys a hint. So to import ADM variables, ADM base X variables, you could look at how we do that from the BSSN recipe, but this is how we can do it for the metric. So I'm just going to reformat this so that we can read it better.
That's a kind of silly question.
No questions are silly questions.
So the reason that you need to correct it, like the metric is flat, meaning it's zero. Like you see how the metric, why not just make it 2x2 and 2D wave equation?
In this specific notebook, yes, the demo EmitCactus notebook, it's a 2D wave equation, but I think EmitCactus only works with 3D stuff, you know, so you have to provide a third dimension, even if that third dimension is zero. So yeah, I mean the hint that I would like to give you guys is this, you know, like how do we get the relevant quantities from a different thorn, right? And this is how we would do it. And of course, if you have any questions, like either online or in person, uh, just ask away and I'll try to help.
So Lucas, this is Bill. Yeah, should my notebook be looking like what you're showing us? Because my version of a EmitCactus notebook looks very different.
So what I am showing you is the solution notebook. So you probably don't have that one, but I just put this here just to, you know, so that people can get a reference on how to get ADM based variables.
Okay.
I did that because our demo notebook for the wave equation, the one you have, doesn't have that bit of information, you know, so just putting it out there. But like I said, in case of doubt, you can always go to EmitCactus. You can go to recipes. You can go to Cottermouth. It's going to be called Cottermouth for you guys. And you can just go to the bssn.py recipe, and that should give you, you know, any extra things that you might want. That's a really complete and featureful recipe.
Okay.
And of course, I guess by the end of the talk, I, you know, just show you guys the solution notebook and how your solution should probably look like. So maybe just another information as a way of hint. The way that I did this in my solution notebook is that I'm calling this whole quantity here inside the braces as the flux. And, if you know anything about flux conservative formulations, you're going to recognize why we're calling this the flux. Jay talked a little bit about this, right? But when we have derivative of something contracted with a vector, uh, we usually call this like a flux conservative form of something. And I'm calling this whole bit the flux. And the way that I am doing this is I am creating a substitution rule for a variable that I've created previously called the flux, which takes an upper index, right? And I am just writing that quantity here. And I am taking the derivative of this flux quantity. And the existence of the substitution rule will substitute it inside the stencils, and the stencils will get expanded correctly when you call derivative of what's in here. You can probably do it differently. This is just, the way that I did it. If you want, you could, expand these derivatives in your head and implement them however you like, but Right. So, how are you guys doing so far? I guess if we have any questions or comments, just ask them away. The point is for you guys to try, but we also don't want too much frustration. So, do you want to say your question out loud, or do you want me to come to you? Yes.
I've noticed. Right. So I also try to see that. Oh, yeah, Sanches. No, that's basically what you do. Right, so you are these. Yeah, so like, there's not another class. I don't go back. I'm always my side. That close, you might not have to say on the pilot, but. Okay, all right. So the competition, you do, right? Okay. Yeah, so we argued them from the server. I guess you said it wasn't bad. Yes, I you should. Okay. But you go here, so my question is. You want to present the network. Yes. I said, no, I said, no, you have to check out everything. Yes. CarpetX is your, okay, so let's do. All right, so that's clear. Yeah, so each of the. Yes, I actually do it. So this is science. This is what you want.
Unified,
but it's
So it's making sense. So EDM base is flat, it's for specific carpet.
yeah,
This is,
this is the CarpetX version of that.
oh, okay.
So if you formally you should recognize an exit. It's just CarpetX version.
Oh, okay. I don't know why that didn't click.
No.
Okay. All right, thank you. All right, this is how.
Yeah, I suspect. They're just updating or recent version. Yeah. GCC or GCC, so then I think it reflects so it's still takes. But so the our version's available. Changed. Is there a compiler version? Okay. I can tell you the patterns. Okay. You have, the tutorials, my second one was, where is EmitCactus? Oh, well, it's, well, okay, so go to the tutorials. That's. ETK1.cct that was. ETK1. You made a login, right? All right, yeah, let me give you the code again. Lot 0.
Lots. That lot, after that.
Yes. Looking block 0. That was the capital. That's your code that gives you forget password it twice. Proof of password you want. Don't use letters, numbers, underscore. Sorry. I know most places want you to have a letter, number, and scroll noise, but we don't have scroll noises.
Okay, letter, number,
And underscore.
Underscore.
The identifier.
got it.
Got menu. Basic group. Menu has one menu. See. Yeah. And scroll down and sort your index like all the inputs. Yeah. And you can ask it for its compiler version just on top of things.
Yeah, it looks like it's using GCC.
Yeah.
Okay, what?
I remember we had a hands-on tutorial like this once, and this was a few years ago, not as many as you would expect. But you, at the time we were using thumb drives and virtual machines, this doctor had quite hard on you. And this one person was saying, I can't get its logo on my machine. I come over, and it's a Windows XP machine. With half a gig of RAM. Oh. I said, no, you just can't do that. It's not gonna save it.
Built for desktops, but not bad desktop.
Wouldn't it be like,
That takes it back.
yeah.
But, when you hate that, you have the metrics that upper. So the way to get was reverse. This is also going to be something very really not explain up. And finally, every time you go upper six, you can substitute. So you can substitute.
Is this session done? Is this?
The tutorial ends at 4:30, and 4:30 to 5:30, so it's fine. And
We don't need all this time. So now. This. After this. For a thorn test. So we. So now, so you see the right equations, you can just use this. Well, right, so to write it to write equation 6, you're going to get all your set up 5. You're going to need gamma G, here gamma. So G and gamma are the same package. Then the field matrix of gamma. So what you do now is some function. They're all in the right hand side. You right hand side. Row and that's our like right that includes
Did you make sure you?
that's what you think one. Yes, going to so for this film doesn't mean all information. There's for against one variable for the state. One variable for the right side. You row right side. Then you're gonna apply BI. BI right side. So then here you just have two variables, B and U. one more. Excellent.
Yeah, no, no.
Yes, but the indices are. We have to order on indices. A, B, C, I, J, K. The campus is there. In that case, you would say L, I, or L, A, whatever. Remember, of course, with the change things here. This way. Yeah. Well, see, you're saying that E is that's it. That's now you have two variables. Sorry. Vectors. And have the greater equals right by the B.
Yeah.
Oh, no. Equals. Function sickness, scales and slides. And the equation you believe actually happen. So here.
See also the
So pretty. So this is the equation actually right the right side. Here, multiply.
figure 15 minutes.
So you probably want to change.
Oh, right.
But once you do that, this is the place, this is what base multiply. So here's what happens. At this, you don't, but at this state, which is everything that's on the back. Right side. So your side, issue is you need to be right state. Right from here at the beginning, look what you declare. B, you declare B and B. The right hand side of B. So that's really something that is going to register. Then, architecture, no. State. Yeah. You know, it takes the place that's going to be better. So time was actually only right. Yeah, murder.
Maybe it's time to transition to giving answers.
Okay.
Because, you know, we got about 20 minutes.
All right, yeah, that's good.
I'm probably not in about for an hour to. In any event, I think, you know, I don't know how many people are working hard or how many people are reading their email.
Well,
You can consider this as the chill out talk. Okay, so as suggested by Steve, we're going to start doling out some answers now. Everybody loves answers. Why is Jupiter doing this? Let me try to refresh.
Sometimes if it starts doing that, just click on something and use the arrow keys to go up and down. It will reset my sanity.
Okay. Excuse me. I think the sanity has been restored in the Jupyter Notebook. All right. So let's start walking through this thing here, right? So we begin by bringing EmitCactus into scope, right? So from EmitCactus, import everything. And we also bring an extra symbol here from SymPy, rational. Now, rational doesn't do much when you emit code with it. It just prevents things that are fraction to be emitted as floating point numbers. So for instance, if you write rational 1 comma 3, you're going to get C code that looks like 1 over 3, not 0.333333 or something like that, right? And from math, I am importing pi because we're going to use pi for our initial condition. Okay? This is just an NRP conditional file updater control. And here we get to the actual thing, right? So I'm defining this arrangement called workshop EmitCactus, and then I have this thorn called the non-flat wave equation, right? And of course, this is a thorn def. It gives me a handle. And I am using that handle to interact with my thorn def. I am explicitly saying that I want a 5-point stencil, meaning fourth order centered finite differences. And next, I declare some parameters. These parameters are going to control some things in the initial data. I am going to use this 2D-like wave, standing wave initial data, right? So I am defining a parameter called SPD for the speed, KX, KY, and KZ. And I
Lucas,
can also, yeah, go
Lucas,
ahead.
this is Bill. Can I interrupt? I think it's a dumb Jupyter Lab question. I
That's
was trying
fine.
to set up globals so that Shift Tab could tell me what these functions were inside of this write file, and
Right.
they don't somehow. I don't know how to set that up. Does your Shift Tab give you what sort of add parameter is or what thorn def is or
I can try. Let me check. Shift tab?
you know how you to
No,
help in Jupyter?
shift tab doesn't do anything for me. I'm sorry about that. I don't know enough about Jupyter functionalities to help you with that.
Okay, yeah, I was trying to define these things sort of globally and thought it might work, but it
Right,
doesn't within these write files for whatever reason. Okay, I'll play
right.
with that.
But if you want to use an IDE like VS Code, for instance, that should you should be able to do what you want with that. It's just the notebooks are more convenient for presentation purposes. All right. So now after I've defined my initial data parameters, I start with some variable definitions, right? And here, like in the BSSN recipe, I am reading some variables from the ADM base X thorn. Now, there was a good question in the audience here. If you're not familiar with CarpetX, ADM base X is the CarpetX equivalent of ADM base, right? It's basically just an interface thorn which defines some variables, in this case, the ADM variables. And it's basically a centralized place where you can read and write your ADM variables to and from, right? So in this case, we're saying that we want to read the variable called G in ADM base X, which in our example here is, the 3 metric. We call it gamma when we're talking in math terms, but CarpetX just calls it G. That's a standard notational convention. Right, and of course, we have to say that this is obviously a 2-index tensor, and this is also a symmetric tensor because it's the metric, right? And we read it from ADM base X. Now, we also need to read the lapse, and we need to read the shift. The shift is a vector, so this is why it takes the UA parameter here, right? Next, we are not really using this, but I decided to do it anyways. So if we ever want to add symmetries to our parameter files, right, this is going to be needed. declaring parities. So we have both scalars and vectors in our code, right, that are going to be evolved variables. So if we go back to our equation, v is a vector, and all the other quantities are scalars. So I am using the parities notation, the standard CarpetX like parity notation to define. I've actually just duplicated that, but I'm defining the scalar parity and the vector parity for our evolved quantities. And like Max said, this isn't explicitly needed, but I am defining the centering for good measure anyway, right? Good. So after that, we define our state. So for every state variable, we're going to need a pairing right-hand side. And the way that this works in EmitCactus is we have right-hand sides as arguments of our state variables, meaning when you declare a variable, you should first declare its right-hand side, like we're doing here, right? So the right-hand side of u, which is a scalar, it has this centering and has this scalar parity, right? And we also have u, right? Has the same options, but the extra option here is that the right-hand side of this variable is going to be u right-hand side. And this is, of course, is going to take care of the ODE solver mechanism required for this time evolution to work, right? I am doing the same thing here for the remaining variables, for rho, another scalar variable. But v, remember, v is a vector quantity, right? So I am defining v right-hand side and v both as vectors taking a lower index LA, right? And here I have the proper parity set. And finally, I am defining this auxiliary variable that I'm calling the flux, right? Which is a upper index vector-like quantity, right? This is not going to be an evolved variable. This is going to be a temporary used in the processing of our equations. Right, next, we construct our inverse metric, right? So given that I've imported G from ADM base X, now I have to construct G upper index, right? ADM base X give us G lower A, lower B. I want to find the inverse of that. So what we're doing here is we're saying, please expand this into a matrix-like object, and then please compute the inverse of this matrix-like object, and also give me the determinant of this matrix-like object and store it in these variables, and make a substitution rule that says whenever you see this, just substitute that by the inverse matrix that I just computed, right? So this is the way that we get G lower index and upper index. Next, I am bringing some coordinates in. These coordinates are more for the benefit of our initial data, right? We are explicitly using x and y on them. Here we defined the wave angular speed coefficient or whatever, which is the speed times the square root of kx and ky. Remember, these are parameters. We just defined them, right? And ID func is just going to be the function that I'm going to use as initial data. And we're going to be taking derivatives of it. So this is why I am storing it in this variable. Right? So now we started adding functions, the actual scheduled functions in Cactus, right? So we are creating a function, and we're going to call it NFWEQ, which means non-flat wave equation init. And we're going to schedule it at the initialization bin. And this is where our initialization is going to go, right? So we're going to add, so u is our main variable. So we're just going to assign ID func to it, unaltered, right? Rho is the time derivative of u, right? And this is what I am writing down right here. V, the three components of V are the x, y, and z derivatives of u, right? So I am writing explicitly here that VL0 should be the x derivative of the initial data, VL1 the y derivative of the initial data, and VL2 the z derivative of the initial data. So Steve says that we could have done this with an abstract index and gotten this written at once. We would have to use capital D instead of diff, but I wanted to use SymPy to compute the derivatives in this case, not. Okay, I Right. So what Steve says is that we could have replaced this by something like this. Oops. Right. So what Steve comments is that we could have replaced these three function calls by this construct. Right. But let's move on. This is where we define our right-hand sides, right? The actual evolution equations now. So again, we give it a name. We scheduled at the evolution bin. And here is the quote unquote trick that I mentioned. I am writing a substitution rule for flux, right? And what I have here is the quantities inside the braces, right? So I have beta upper index times rho. Oh, well, sorry. I have, square root of the, God, square root of the determinant of the metric divided by alpha times everything in the parentheses, beta upper index times rho plus alpha squared plus whatever h is, right? This little guy right here, right? Just substituting it back here and closing parentheses back again. So what's going to happen is I'm going to have a stencil call that takes a derivative of flux, and all of this is going to be replaced inside that call, and the derivative stencil, the div call, the derivative call will know what to do when it encounters this object, right? So the right-hand side for u is just rho, super simple. The right-hand side for rho is beta upper index contracted with the derivative of rho, again, super simple, plus alpha over square root of the determinant of the metric times derivative of the flux, right? And here we have flux and the derivative of the metric contracted over this index upper A. And finally, for our vector-like quantity v, it's also a simple quantity. We have v right-hand side. It's just a derivative of rho with respect to that lower index. And this is the end of the recipe. So this recipe generates an evolution thorn for this set of equations, 5, 6, 7, and 8. Right? Now, the rest of this notebook is just, the usual song and dance of linking that to something that Cactus can see, compile, run, and visualize, right? So this is the output you get during EmitCactus's generation routines, right? It's going to tell you exactly what it's doing, the equations it's using, la, la, la. It's a big output, right? Here we are just, this is based, the section from here on out is just based at the EmitCactus.ipy notebook that everybody should have, right? This is just linking the new thorn against the cactus build system, building the thorn, right? One major change that we have here in our recipe, in our parameter file to run this thorn, is that now ADM base X needs to be part of our list of active thorns because we are reading variables from it. I just decided to change the integrator to RK4. I am making sure that we are using the correct number of ghost zones. I set up a grid that extends from -20 to 20 with 80 cells. But that's you guys can play around with that, right? You can. Yeah, I wanted to call your attention to that, right? So what options do we have here for a flat metric? Well, ADM base X doesn't really give us anything besides the Minkowski flat metric, right? So an interesting thing for you guys to try and do is to write a thorn that actually sets up different initial data than flat metric, right? So you can see, for instance, in our EmitCactus Cottonmouth BSSN set of notebooks, we have a Kerr Shield ADM base X initial data writer, right? But what we're doing here with this file is we're just bringing in the standard Cartesian-Minkowski initial data metric. Now, there are no other official initial data writers except for two punctures X. But two punctures X is not part of this cactus installation you guys get here. So I tried using two punctures here, but you guys don't get two punctures X installed. But in principle, the initial data could be anything, right? And after that, we're just compiling the thorn and visualizing our output. I just need to, so we're using Quibbit again to plot our function, right? What we're plotting here is the U variable or main state variable. And I guess here we get, unsurprisingly, we get a standing wave that shifts up and down, right? And I guess as like I said, like as exercises for the reader, where things that we can try to do is we can try to modify these initial values, and we can try to come up with some more interesting and possibly more complicated initial data and see what happens, right? Writing initial data using EmitCactus is not hard. You just have to write to the proper ADM base X variables at the proper schedule bin. Like I said, if you guys look, if you guys look here, for instance, we have an example of doing that for the curse shield metric, right? Basically, I am just the same song and dance, reading the variables, and here I am defining all the quantities that you need for the curse shield metric in isotropic coordinates, right? And then we're just writing them back to, right? We just write them back to ADM base X at the ADM initial data group, right? That's as easy as that, right? So you could combine these things and get a more interesting non-flat background wave equation. But the takeaway from this is, trying to learn how to do something that's like a step above from the wave equation in the sense that we get to use some tensors, we get to use some vectors, we get to declare some parities, and we get to worry about things that just scalars don't let us worry about. So I guess this basically concludes it. If you guys have any questions or comments, I guess this is the time for that. But otherwise, I guess we're done.
So Lucas, right in the middle there, it says something about Sprant 5, Sprant 5. You're writing files over there. Looks like I am too.
Sorry, what?
So right in the middle of your notebook, it's putting these output files in Sprant 5, not in your home.
Yeah, so while we were giving the previous talk, I asked Steve to make sure that this notebook is running, and so probably this is why you see some of his names here, right? We got the me and him mixed, right? Yeah, right. I mean, because the notebook saves. Yeah, I mean, Steve was doing some runs just. Yeah, I mean, but it's it's
That's
fine,
fine.
right? That's why you get that. Yes.
It's like the previous one, I think it was set up in CarpetX.
The question for the audience was, do we use EmitCactus to set up boundary conditions? No, we are using CarpetX's boundary mechanism to set up our boundary conditions.
Give support for new red X.
Oh, right. Roland asked if we have support for NeoRedX. Not yet, I don't think so. We have to think of good ways to incorporate that both into DSL and on our recipes, how to use that thorn explicitly. All right.
Yeah. Seems to be working fine, just reaching.